Hey guys, this is 18.1 through 18.4 for our physics lessons, and we're going to start to introduce concepts essentially like the electric battery and electric circuits. And so there's some really cool stories in here that you can read about Galvani and Volta and this idea of where electricity was first discovered and what it was initially thought. Galvani, he thought that he had created life force by sticking different types of metals into frogs' legs and making them twitch. He was pretty excited about it. But the first thing you need to understand, Galvani, you can think of galvanized steel, definitely did some really cool stuff. You have to remember that the guy went to this university right here. It's called the University of, I'm sure it's pronounced differently in a different country, but here in the U.S., that would be pronounced baloney. So you know he was full of it. I'm just kidding. But that's just kind of laugh for a minute for me. All right, thanks. Okay, so anyway, in our Volta went on to disprove that the material, that the life force he had created was actually just a reaction between the different materials, the different metals, and so he built the first batteries, the first what we consider electrode batteries, and today we have batteries that are pretty similar. In structure, they have the same kind of behavior with a positive and a negative terminal with an electrolyte in between them that allows the travel of electricity to flow. But what we're really going to get after is a couple of things. We're going to start with this concept of electric current. Okay, just so that we're clear, batteries are going to be labeled or drawn with this symbol here. That's the symbol of a battery with a positive terminal on the long side and a negative terminal on the short side. Remember, a capacitor was two parallel lines that were equal in size, whereas a battery has the different length there, positive and negative. And even though we eventually figured out that it was negative charge that flows, batteries have always been labeled that current flows in the direction of positive charge flow. Again, we know negatives are what actually move, but just out of habit and tradition, positive charge flow is the direction of current. And this definition for current, okay, I equals, so current equals the change in charge over the change in time that passes through a certain area. The unit there is an ampere, named after the French physicist André Ampere. And so an amp is 1 coulomb per 1 second, and that equals a capital A for an amp. In order for current to flow, or charge to flow and create current, the circuit has to be on a closed loop, meaning that there's no disconnect from one end to the other. If I come through and I break the wire, I cut the wire, I can't flow current. Even if I'm touching the terminal, have something touching the battery, it won't release the flow of charge. So that's the first thing that you need to know. So you can see that in these diagrams. If you're not connecting to the positive and the negative terminal, the light won't turn on. Here we have an example where we're touching both terminals, so we're going to have charge flow, whereas the others do not. One other symbol that you might want to be aware of, if you ever see this symbol, we won't work with it a ton in this class, we're just introducing stuff, but that is the symbol for ground, which usually means we've grounded it literally to the ground, to the earth, or to some other object that will prevent us from having a charge of flow, or a flow of charge through a human body or something like that, where we can ground it out if we need to. The second is what's called Ohm's Law, and this is probably the most fundamental law you need to walk away with out of this chapter. While we need to know what current is, we need Ohm's Law to solve so many problems. And it basically says that through any resistor, and we're going to use this Charlie Brown symbol to represent a resistor, okay, through any resistor, if we have a current flow, okay, flow through there, the voltage drop, okay, or the voltage loss as I go through that resistor, okay, will be equal to V, the voltage will equal the current times the resistance of the resistor. And that will be something that we measure in ohms. So R will be measured in ohms. Now, putting an O at the end of a number like 36, that would be really confusing for people. And so we had to do something other than an O for ohms. So Greek letters, the Greek letter we chose to go with was the one that sounded the closest, which is omega. And so when we write ohms, we use the Greek letter omega, which looks a little like a horseshoe. Now, that was a bad drawing of it, but you can find it down here as well. But that is Ohm's Law. And you can see the horseshoe right down here. There's our ohms. Okay, and so we can use those to connect resistance and voltage and current. You can see resistors all over circuits, and they use a color coding striping system to represent the value of the resistor in case you can't see the labels or it's hard to print a small label. These color coding allows us to tell if it's 1,000 ohms or 2,000 ohms along the way. We won't do, again, a ton of that, but when you get into a circuits lab in college, that's something you'll want to understand and spend some time doing. And the last thing is recognizing that different materials have different resistances that are structured in them. While a light bulb functions as a resistor, the wire itself also has some resistancy or some resistance. And so we want to know if I run a long cable, maybe I have my one light bulb, but I run my long cable and maybe here's my battery. Maybe this right here has 3 ohms of resistance. But what about all of the losses that are going to happen along the way? Just due to the wire. The wire is, well, it does allow for the flow of electricity. Kind of keep in mind, guys, that if you think of a wire, copper wire, right, that there's all these electrons in here, and we're trying to send a signal down the line. Well, the bigger the pipe is, the easier it is to flow electricity, but also the type of material it's in. Is it going to be easy to flow electricity or not? And so we have what's called resistivity, and if we want to know the resistance of, say, a length of wire, the resistance of our wire will be rho, the resistivity of the material, proportionality of resistance, times the length divided by the cross-sectional area. So you could imagine this is the length, and this right here out on the end, that would be the area. Okay. Now this rho, it's not the density, but you could have an argument about like how is it connected to density. It just has to do with the specific material that we're working with. And so you can see that copper has a resistivity of 1.6 times 10 to the negative 8th. And that's a pretty small number. Silver is 1.59 times 10 to the negative 8th. The lower the resistivity, the better it's going to conduct electricity. You can see that when we get up to things like glass, it's 10 to the 9th to 10 to the 12th. That's a big number when you compare it to 10 to the negative 8th. Okay, and obviously some of these things do have a temperature dependency. We're not going to talk about those in what we calculate. Will be pretty simple today, but resistivity is measured in ohms per meter. It's how much resistance you get every meter. And so, yeah, so that's how you calculate the ohms times meter, sorry. That's how you calculate this guy right there if you're looking for the resistivity. But the resistance itself will be measured in ohms like anything else. All right, hopefully that helps you get through the questions and understand the concepts there. We'll see you guys in class.